There were two bits of pre-release material referenced in this question. This is the first one which we already used in the exam. The key bit though for question 3 was this. And it tells us about payback time in years and some key facts here. We'll look back at this in a moment when we get to that part of the exam questions. There's also this information about electrical energy. Wasn't essential, but it did give you a bit more of an idea of what a kilowatt hour was. And I think that background knowledge can really make a difference when it comes to questions in the exam. First couple of bits people did pretty well at. We had to find out by how much the average cost to produce 1 watt of power from a solar panel dropped by between 1975 and 1995. So it's just reading from the table and taking that away, just $95. They then talked about this rule called Swanson's rule. Name's not important, but we were looking for this. So 1 watt of power from a solar panel decreases by 20% when the total power generated doubles. So we can see here it doubles, and we can see here it decreases by 20%. Same as multiplying it by 0.8. So we wanted those 2 years there, 1985 and 1990. And they're the only 2 possible years that followed that pattern. This next one, quite a few people struggled with. So trying to find out if there's enough sunlight in Glasgow to get solar panels. And we had to use the chart and some estimates. And when you see this in a question, it wants you to write down at least one estimate, make it really nice and clear so you can get the marks for that, to work out a rough figure for the yearly total solar energy per square metre in Glasgow. So a couple of different ways you could do this. First of all, you could say, well, let's take an average of what's on the chart here. And I'm going to say that average is about 3. And that's 3 kilowatt hours, and that's per day. I could then multiply that by the number of days in the year, and I could round that, could have done it by 370 or by 400. And that gives me 1,086 kilowatt hours a year. And you don't get penalised for this, but it is quite good to round that. Because I've taken this 3 as such a round figure, we could say that it's going to be about 1,000 kilowatt hours a year. That's one way you could do it. Another way is to look at the totals of each of the columns. Quite a few of you did this. You could add up all of those. And the mark scheme gave you between a total of 37 to 41 for the total of those. Now, that's 1 day each month. So if we then think about an assumption, an estimate with this, we're going to say there's 30 days in each month. And it is important you state this. So whatever your figure, say your figure was 40 just for ease, multiply that by 30 to get the kilowatt hours a year. And a few of you got the first marks here, but then multiplied it by something different at the end, maybe by 12 months or by 365 days a year. And you're allowed on this an answer between 730 to 1,460 kilowatt hours. But if you just put an answer down in there, you'd only get one of the marks. It's important you show your work and you show your reasoning, you show any estimates or assumptions with that. For the next part here, you just had to get 25% of your answer before. Easiest way to do that, if I take this 1200 answer here, 25% is just a quarter, just divided by 4. Didn't matter on the method there. Didn't matter if your answer was outside of this region, as long as you did accurately find 25%. That got you the mark. We were given a lot of information in this question, and it's this that we're looking to calculate. That if the person goes ahead and has the 8 solar panels fitted, we're told the cost of them here, what will the payback time be? And we need that to the nearest year. So after how many years will she start to make a profit from these? From the pre-release materials, this really helps. So we can see from here the payback time in years is the total cost of installing and maintaining. This example is double glazing, but it holds the same for solar panels. And that's dividing by the annual saving. So they're the two things we need to work out first of all. So the total cost will just be the 6,000 to buy and install, plus the 3,000 payment for maintenance and insurance. We then need to work out the savings made. Now it says a year there'll be 2,800 kilowatts and all of this electricity will be used. And if you'd bought it from an electricity company, it would cost you 14.05 pence. So let's calculate that. Might just do that as pounds to make it a bit easier. So that's how much savings made per year. So to work out the payback time in years, we just need to do our 9,000 divided by this. You could round it here, you wouldn't get penalised if you didn't, and that gives 22.9 years. So because we want it to the nearest year, we've got to round that up, that would be 23 years. You could have stated in here that you thought she shouldn't buy this and calculate it that way, which would come to an answer of 16 years, but you did have to state clearly that you weren't including the insurance in that. The next part here was why might the payback be less than we've just calculated? There's different reasons, but in the pre-release materials, it said fuel prices may have risen. And that makes sense here as well, even though we're looking at solar panels. The last one was calculating interest. So she needs to borrow £2,000 and she's got to make 12 monthly payments of £44.71 for 4 years. So we need to work out what her total payments will be over those 4 years. And lots of you stopped at this point and lost the mark, but we're after the how much interest. So from that, we've got to take away the amount she borrows, and that leaves the amount of interest.